You see, we have got two types of devices. One are handheld, like tablets and phones. Others are like laptop. And we know that they have a different family of processor. This one, this is Samsung phone. Which processor is inside it? Snapdragon. This is a Dell machine. What processor is in it? Intel. These are two different companies. They are doing different things, and they are making two different processors. The both processors are doing the same. They're executing programs for myself, isn't it? But they belong to two different school of thoughts. It's like both are doing the same. Ultimate results are same, but they both are belonging to two different school of thoughts. Those school of thoughts are RISC, reduced instruction set code or reduced instruction set computer, and the other one is complex instruction set code or complex instruction set computer. Mainly we call it what does that mean? Let's see. See, so RISC versus CISC, complex instruction set computer and reduced instruction set computer. Complex instruction set computer is unlike what you have learned in von Neumann architecture and assembly language last year. So if it is reduced instruction set code, it means that we have to write many number of instructions to get this job done. Whereas in complex, we would have to write less number of instructions. For example, I've got these instructions. LDM63. Load to accumulator what? 63. Add 64 to it. Whatever the result, make a product with 29. And then product it with R4. What is R4? The register. Whatever the content of register will be multiplied with the content of accumulator, and the result will be placed in accumulator, and then you store that to address in memory. You write back it to memory at address 23. So how many commands are these? 1, 2, 3, 4 and 5. This is said to be reduced instruction set code, means you have got smaller instructions. Whereas in complex instruction set code, all you are doing is multiplying 23 with 29, and then you are adding 63 with 64. These are addresses, these are actual constants. And then whatever the result is, that will be multiplied with the result of 23 multiplied 29, and then it will ultimately be, oh, sorry. This one is the memory address where it will be written back. So the result of 63 plus 64 will be multiplied with 29 memory address, and then the content of register R4, and the result will be written back to 23rd location in the what? Main memory. You can easily see, you don't have to remember these commands. I'm just trying to tell that in complex instruction set code you write less and you get more, whereas in reduced instruction set code you have to write more. Alright? So the size of the instruction is fixed. Remember the word size from AS. If it is 32-bit computer, you have opcode and operand. Opcode के लिए आपके पास you have got 20 bits, and for operand you have got 12 bits out of 32-bit register. It is a ratio of 5 to 3. It is a ratio of 5 to 3. If it is 60 board, that 20 becomes 40 and 12 becomes 24. It's still the ratio is. So opcode and operand. So this is fixed size instruction set. If you have got an opcode bigger than that, you cannot avail it because you don't have a space for it. But over here, it is flexible. It is flexible instruction set. So that flexibility and larger instruction gives you an option to write less. And here, no flexibility, fixed size instructions, shorter instructions. It actually pushes you to write more for the same output. So you write less for complex instruction set computer and you write more for reduced instruction set computer. But everything ultimately boils down to what? Binary. When it comes to binary, no matter what it is, it is the same. Over here, this one instruction has a relationship of 1-to-1. Every assembly language instruction has an equal machine language instruction. Remember from AS. But over here, one complex instruction has the relation with the machine language 1-to-many. So who does it? Ultimately, this would be done. Who would do it? The processor itself here. So let's see how it works. So shorter code, and here we have large code. And then compiler does less. Why compiler does less? Because it has less to do. All it has to do is to convert your instruction to equivalent binary instructions. Over here, favorable for high level languages because you have to write less, and less efforts for programmers. But if it is reduced instruction set code, compiler does more because it has more instructions to deal with. More efforts for the programmer because programmer would have, this is one very important thing. In reduced instruction set code, the number of instructions that you have is less. You have a set of instruction which is quite shrinked. In complex instruction set code, you have a larger number of instructions. It's complex and larger. It is reduced and smaller. So you have to put more efforts to do the same as was being done in complex instruction set code. So more efforts for programmer. I told you that whatever being done here is also being done here, but how? Your processor, this is your processor. The code that goes to processor is complex. Even in binary form, it is complex. And computer cannot do so many things together. Computer can do only one thing at a time. Even if the binary code is complex, computer would have to break it down into number of smaller ones. Here, you are doing it yourself. Over here, although you are not doing it, but what is happening? Processor is doing it for you. So yeah, this is called microcode. So your complex code is converted to microcode. Over here, you are writing microcode yourself, sort of. So every processor has a firmware. You might have heard of it, firmware. Firmware is the program which is made by the manufacturer of that processor. It is embedded inside the processor. Intel might be doing it. So processor does more. Why? Because it has to break the complex code into microcode. And here processor has to do less. Processor has separate. Now processor has separate circuits for every instruction. Over here, one instruction is being broken down by the firmware into microcode, but over here, the processor has got separate areas for dealing with separate instructions. All right, and that makes sense that if you have got separate areas for separate instructions, you can have not a large number of instructions, because large number of instructions means large separate areas for every instruction. That means a large processor size. So we have less instructions, so that we have less dedicated circuitry areas in the processor. That means less number of instructions, means more effort for the programmer, means compiler is doing more, but yet the output is same. So processor is doing less here and processor is doing more here. Processor does less. High heat generation. Why? Because processor is working more. So more heat. So such type of devices like laptop has got what? Cooling fans and cooling, what do we call it, that thing that we put on the top of processor? Cooling, I don't know. Put on side. Heatsink, yeah. Cooling mechanism. We use heatsink then. But does this device has any fan in it? Its body is good enough to cool it down. So you can understand now that which sort of devices have what sort of processors. Right? The one which is heating up, the one that has heat sink, the one that has neon gas going inside it, cooling it down while you are playing game, the one that has fans inside it are of what type? CISC. And the one which is handheld like this, does not have any fan in it, its casing is good enough to cool it down, are mostly what? RISC. Alright? So this requires cooling mechanism, less heat generation. Casings are enough to pacify the heat. These are desktops, these are portable devices, bigger instruction sets. This is irony. It is complex, you have to write less, and yet then you have a larger number of instructions, because that does not require you to have more circuitry. The same circuitry is actually converting everything to microcode. But over here, you have got separate circuit for every single instruction. So you have to have a larger space to accommodate it. So we cannot, so we have less number of instructions here. Memory to memory. You don't have to actually, what we do, we actually load from memory. We have got LDM command, LDD command, LDI command, LDX command, LDR command. What these commands are doing in AS, they all are bringing data from memory to microprocessor, processing it there and sending it, writing it back to the memory. So we have to load it, work around it, and put it back. In what? RISC. But in CISC, all you have to do is to tell that at what memory address what to be done. It is being done by it automatically. So it is memory to memory, means load and store back is part of it. You don't have to tell that load karo and फिर इसको treat karo और फिर write back karo. Over here, you have to actually tell that to load it to the microprocessor accumulator, work around it, keep it in accumulator, and then write back. It works memory to memory, it works register to register. Complex production, obviously, when you have such complex, so you would have a production, I mean manufacturing process. The production process would be complex as well. And then it is expensive as well. Over here, processors are not that expensive. So, have I made myself clear? You don't have to remember all these points. Few of them. What sort of question you would have? Either you will be given a scenario, you would have to judge that what sort of processor is being used, or they will mostly they will ask by what is the difference between RISC and CISC. Okay, there are other points as well. Let's see. In CISC, single instruction is executed in multiple cycles. What is cycle? We know one Neumann architecture, that fetch, decode, execute cycle. So if we have got an instruction that is having an equivalent machine code instruction, it means that it is just one cycle which is required to complete that. But if we have one complex instruction that is passing through the firmware to get into microcode, then microcode is being executed one by one. It means that one single instruction will be processed in number of cycles. So in CISC, single instruction is executed in multiple cycles, whereas in RISC, single instruction is executed in single cycle. By the way, this single instruction, single cycle thing is just fictitious. For example, if it is LDI, LDI will be completed in 3 cycles. Uses control unit. Why control unit? Because it has to actually see how everything is going on. I would appreciate if you don't relate it to von Neumann architecture knowledge, because von Neumann architecture is too ancient. If you relate it to current architectures, even the simpler architectures nowadays do not match with von Neumann architecture. So this is a new style of working, new latest thing. So you don't actually, von Neumann architecture does not lie anywhere, neither in RISC or CISC. It is obsolete. So uses control unit, multi-clock cycles per instruction, and separate units for every instruction, so single clock cycle per instruction. Is that understood? All right. Lately it had become too much complex. So if you could remember a few things from the start. Okay, all these slides are uploaded. Any question? Yes. Obviously, because it needs microcode. Obviously, you write less, but ultimate code would be higher. So you need more space for that as well. It is complex, it requires more memory, it requires higher speed of the processor, it requires more number of cycles, more strain over the processor, more heat, cooling system. It is complex, all the way complex. Yes. I said that it is a school of thought. IBM is basically a cause of so many things. It used to be reduce instruction set code. IBM came up with this idea of complex instruction set code. Later, nowadays, it is neither RISC or CISC. This is hybrid. The one that I have in my laptop, which is i7, is hybrid. Means it has got both abilities. But the one that I have got in my cell phone is purely RISC. All right. So, what's the benefit? Ultimate benefit is to us is whether we are using this complex instruction set code or reduced instruction set code does not make any difference because we are still downloading programs and executing them. Yes, one question would be legit. That is that reduced instruction set code is too simple. How does it work at the speed of complex instruction set code? The answer is speed. By improving upon the speed of processor, they are overcoming the shortfall of number of instructions and higher time to get execution done. So they are improving on speed, so the weakness is being subsided. So whether you go for this or that does not matter. We have to choose for the device, and device is working fine for us. You might have heard of this Chromebook, might have heard of such devices which are making use of RISC based processors. ठीक है ना? So it is being tried whatever people like, but there are two school of thoughts. All right, and they both are serving the same way for us. You may go back home and you can research more. Okay, but we don't need to discuss it anymore. It's just like two or three questions. What is risk indices? What is the difference? And what are the benefits? Why do we use heat in here?